Okay, thank you, Kasura. So,
okay, thank you, Kasura, for the great talk, walking through this hardware stack we have at AQT. So, and thank you everybody for the opportunity to have me here, and let me introduce you to our new flagship quantum processor architecture. I'm Roger from the Advanced Quantum Testbed. So I'm here to highlight, sorry, wait one moment. I'm going to highlight just two keywords here in the title, which summarize the main features of our new quantum processor architecture. So this is what people normally think of modern multi-qubit quantum processors looks like. It's basically a lattice of superconducting qubits with well-defined Lewis-Liber interactions. If you want to entangle any arbitrary qubit pairs on this lattice, you can use a chain of appropriately designed two qubit gates with Lewis-Liber interactions. However, in the LISC era, we all know that those two qubit gates are not perfect. So this directly to the fact that the overall fidelity for entangling arbitrary qubit pairs become exponentially more expensive. So this limited the functionality of such hardwares by their low-level connectivities between qubits. So we here at the Advanced Quantum Testbed, we provide a solution to provide shortcuts between all the superconducting qubits, and by embedding a reconfigurable connectivity graph into the hardware itself, into the quantum processor itself. And this is greatly minimize the cost associated with entangling a large group of qubits simultaneously. And we call such hardware or such architecture the SpiderNet architecture. Sorry about the heading. So, SpiderNet architecture, and it's important for us to realize to also improve or mitigate the challenges posed by the increasing density of wirings inside this quantum processor. Namely, we want to maintain the controllability over superconducting qubits and reduce the level of crosstalks. And we do that, as I will introduce in the following slides. That we created the enabling technology allows us to use 3D integration to mitigate the crosstalks issues and increase the controllability for individual qubits. And this research is coupled with thorough finite element simulations that help us understand the electromagnetic environment inside this quantum processor, and help us and guide us to design the quantum processors in the best way. So let me step back. As I mentioned, one of the main features of our new quantum processor architecture is 3D. And let me ask this question: why we need the 3D? Because I mentioned in the last slides that we use 3D to be able to route our signals more efficiently inside our quantum processor. Just like dealing with traffic issue with your everyday life, and as you have more and more roads, you encounter the geometric constraint of a 2D surface. You have to go to a third dimension in order to route your traffic. In our case, signals more efficiently. And similar idea was already being used by the IC industry for the last few decades. As you can see in your cell phone, they're being able to couple billions of transistors with this kind of microstructures efficiently on a daily basis. And unfortunately, we cannot directly employ their techniques because we do pay attention to the single photon loss levels, and we have to reconstruct or recreate this technology from ground up to make it quantum compatible. And second reason for 3D is that we want to use appropriately designed microstructures to tailor the electromagnetic environment such that we'll be able to suppress the crosstalk levels between densely packed elements. On the left-hand side, we run finite element simulations of a scenario where you have a meander resonator sitting on a silicon chip, and we put another silicon chip with one surface fully metallized on top of this chip, and those two chips are connected together by this light blue superconducting channels on the left-hand side. And this light blue superconducting channels are also reflected as these black dots in this finite element simulation domains above it. You can say that this light blue is kind of superconducting channels form a lateral Faraday cage that localize the fundamental modes energy distribution around the meander resonator. And so the extent is much smaller compared to its extent in the substrate. And so this means that you can pack your elements denser and closer together without worry about too much about the crosstalk between them if you design this Faraday cage appropriately. And on the right-hand side, so we simulated another scenario where we try to understand the crosstalk between the waveguides, the control wires that carries your quantum signals and the coupling and the signals and the single photons. So we numerically inject the signals into this red trace, and I want to measure numerically the crosstalk amplitude and signal amplitude you can get from the blue trace and from the black trace at a variety of distances. And we plot out the simulated results in lower right in this figure. You can see that, of course, the crosstalk amplitude, both of them scales down with the distance, but you can notice that over a larger range of distance, the blue trace has orders of magnitude smaller crosstalks compared to the black trace, meaning that so these two facts combined together means that with a carefully tailored electromagnetic environment and using 3D integration, you'll be able to decrease your level of crosstalk to a level that you can pack sufficiently complicated wiring together and work and have still maintain good control of your quantum system. Third part is more practical and towards the fabrication side. So there are a variety of different choices of 3D integration, and if you choose with a proper choice, you can be able to separate the fabrication of your quantum processor into two parts, depending on their functionality and the fabrication requirements. As I'm showing here on the left-hand side, you can fabricate your superconducting qubit with your best calibrated and pristine fabrication technologies, and keep its high coherence and as robust as possible. On the right-hand side, you can add all the complications to the other chip, like use what kind of 3D microstructures to help you with the wiring and the crosstalk mitigation, and even use the TSVs to help you with interfacing with the external electronics that you want to access. So after fabrication, you just bond these two chips together, and you can literally get the best of both worlds: the robustness of a superconducting qubits and the functionality required for the wiring. And of course, the last part is more like for the future reference. I mentioned that with a proper choice of 3D integration, you'll be able to separate the fabrication into two pieces. And you can keep your best and most pristine fabrication technologies for fabricating superconducting qubits, and keep its high coherence and keep its robustness. Actually, on our chip, you can play all kinds of interesting and innovative techniques to make it more exotic even. So in that case, you can substitute, for example, the other chip by other platforms even. You can integrate the nanophotonics and the photonics into the other chip and combine it organically with your superconducting qubit chip, and so that your superconducting qubit chip can be able to interface with other domains of physics more efficiently. And the proper choice of 3D integration in our case is this kind of flip chip technology, which basically means that you separate this one processor into two pieces, depending on their functionality and the fabrication requirements, and you stick them together. And in this slide, I'm going to highlight this critical important element, which is what we call Indian bumps. It's a red rectangle shows that. The Indian is pretty much a very ideal metal. It's a superconducting and it's soft. So it means that if you compress in very hard together, they tend to stick together. This means that this Indian bump can be a very good galvanic connection and also mechanical connection between the two chips. And of course, we also have a spacer highlighting this blue rectangle that's used to define the spacing between two chips to the nanometer accuracy. And this forbids your chip from collapsing together as you compress it in together. So this research is separated in two parts. One part is the design and the simulation of our quantum processor. The other part is the fabrication development. So the fabrication, before the lockdown happened in March, we developed the 3 critical pieces of technology that enable us to fabricate our new quantum processor, which are the Indian bumps, the hard spacer, and the aluminum air bridges that's used to connect different parts of the chip together on the wiring chip. So this is what our Indian bumps looks like on a test resonator chip. And this is what our hard spacer look like. it provides a nanometer level accuracy in creating a spacing between two chips. And after walking through the enabling 3D fabrication technology, let me switch gear and talk about the design and simulation of and the running principle of our new quantum processor architecture. So the layout schematically is shown here on the left-hand side. And as the name suggests, it's a SpiderNet A. So we have 8 qubits on it for our first generation SpiderNet architecture. And the wiring chip contains all the controls, as I mentioned. But it has one particularly important piece of element. It's this coupler bus. It's basically a multi-mode meander resonator. And we are going to use its 8th order mode to mediate the coupling between all the 8 qubits. One particularly important element attached to the bus is that there are 2 square loops to the ends of the bus. We're going to use it to dynamically change the boundary impedance so that we can be able to modulate the bus on the fly, as I'll mention later. So you can simulate the 8th order mode, the high order mode of this bus that we use to mediate the coupling between all the 8 qubits in this blue box above the skin. Excuse me. And you can plot out the voltage profile along its distance schematically with these black lines. You can see that we strategically placed all the 8 qubits at the voltage nodes of this voltage profile of this high order mode of interest. This directly leads to questions that you started with 0 static coupling and how you're going to mediate the coupling between all 8 qubits. The reason is that we're not going to use a static coupling between the qubits and the bus to do the mediation. We're going to actually inject signal into the square loop, and we'll start to modulate the bus mode profile back and forth. So your qubits will see a modulated coupling to the bus resonator mode. And in this way, if you modulate the mode profile and the coupling appropriately with the frequency matching the detuning between the second and say the 8th qubit, you'll be able to induce these swap interactions between the second and 8th qubit, similar to the one Ravi mentioned for the parametric gates. Actually, this is a parametric gate. And of course, the power of this scheme is that you are not limited to only one frequency tone. In fact, you can inject as many frequency tones you want to the modulation signal for the bus mode profile. You can, it's only constrained by the room temperature electronics. So in principle, you can literally just on the fly encode the connectivity graph directly into your spectrum of your drive, and you can change everything on the fly also very fast. So the chip is being fabricated in partnership with our friend in MIT Lincoln Lab during this lockdown, and also our chip gets shipped back to us. We'll start with benchmarking and run interesting experiments on it. Of course, at this point, we welcome the collaborations and ideas from the industry and the academia. That's we can use this idea to explore explore what can be done, all the possibilities of this first generation SpiderNet architecture. So last but not least, let me thank the whole team, especially the 3D team and the MIT Lincoln Lab, who help us greatly in enabling the fabrication of this new quantum processor in this very difficult time. Thank you very much.
Okay, thank you, Roger. Molly, I think that's your cue to take it from there.
Alrighty. Can everyone see the presentation?
Yes, it's good.
Excellent.